Modern benchmarks increasingly attempt to measure robustness, generalization, and reasoning rather than simple pattern recognition. One major development in recent years has been the rise of multitask benchmarks. Instead of evaluating a model on a single dataset, these benchmarks aggregate performance across many tasks. The motivation is to reduce overfitting to any one task and to better approximate general intelligence. Multitask evaluation introduces its own challenges. Tasks may have different scales, metrics, and difficulty levels. Aggregating them into a single score requires normalization choices that can influence rankings. Weighting schemes can implicitly prioritize certain capabilities over others. Sophisticated users must examine the per-task breakdown, not just the overall score. Another important trend is the shift toward more realistic and adversarial evaluation. Early benchmarks often contained annotation artifacts that models could exploit. For example, certain words might strongly correlate with particular labels due to dataset bias. Modern benchmark creators attempt to remove such shortcuts through adversarial filtering, human-in-the-loop validation, and out-of-distribution testing. Robustness benchmarks are particularly important. A model that performs well on clean, in-distribution data may fail catastrophically under small perturbations. Robust benchmarks test sensitivity to noise, paraphrasing, domain shift, or adversarial examples. For deployment scenarios, these robustness metrics may be more important than raw accuracy. Another dimension is efficiency benchmarking. As models grow larger, raw performance alone becomes insufficient. Researchers increasingly care about compute cost, latency, memory footprint, and energy consumption. Some leaderboards now track performance per parameter or performance per flop. This reflects a maturing field that recognizes practical deployment constraints. Reproducibility is another core concern. A credible benchmark ecosystem requires that independent researchers can reproduce reported results. Unfortunately, this is not always straightforward. Differences in preprocessing, random seeds, hardware, and training schedules can produce measurable score variations. High-quality benchmarks often provide reference implementations, evaluation scripts, and standardized data pipelines to reduce this variability. Hidden test sets are a common mechanism to prevent overfitting, but they introduce trade-offs. When test labels are hidden behind an evaluation server, reproducibility becomes harder because researchers cannot independently verify results. When labels are public, overfitting risk increases. Designing the right balance remains an open challenge. For language models, evaluation has become especially complex. Traditional metrics like perplexity capture next token prediction quality but fail to measure reasoning, factual accuracy, or alignment with human intent. As a result, many modern benchmarks rely on task-based evaluation, such as question answering, code generation, or multi-step reasoning problems. Human evaluation is also increasingly used, particularly for generative models. Human raters judge helpfulness, correctness, or coherence. While this can capture qualities automated metrics miss, it introduces subjectivity, cost, and inter-rater variability. Carefully designed annotation protocols and statistical aggregation methods are required to make human evaluation reliable. Another sophisticated issue is data contamination. Large models are often trained on massive web-scale corpora. If benchmark test examples accidentally appear in the training data, the evaluation becomes inflated. Detecting and preventing contamination has become a major concern in large-scale AI evaluation. Some benchmark creators now actively filter training data or design dynamically generated test sets to mitigate this risk. Leaderboards also influence research incentives in subtle ways. When a benchmark becomes prestigious, even small improvements can attract significant attention. This can lead to diminishing returns research, where large amounts of compute are spent for marginal gains. The community periodically debates whether this dynamic accelerates or distorts scientific progress. There is also the question of benchmark diversity. Many widely used datasets are dominated by English text or by images from certain geographic regions. Models optimized on these benchmarks may underperform in other languages or cultural contexts. Increasingly, the field is recognizing the importance of multilingual and multicultural evaluation. From a systems perspective, maintaining a leaderboard infrastructure is non-trivial. Evaluation servers must handle submissions, enforce rules, prevent test leakage, and ensure fairness. Some platforms allow unlimited submissions, which can accelerate leaderboard overfitting. Others impose submission caps or require code review. Each policy choice involves trade-offs between openness and robustness. An emerging direction is dynamic benchmarking. Instead of a fixed test set, the evaluation data evolves over time, sometimes generated procedurally or collected continuously. The goal is to make overfitting harder and to better approximate real-world deployment conditions. However, dynamic benchmarks complicate reproducibility and historical comparison. Another important concept is benchmark transferability. A model that performs well on one benchmark may not generalize to related tasks. High correlation between benchmarks is not guaranteed. For rigorous evaluation, researchers often examine cross-benchmark generalization to understand whether improvements reflect genuine capability gains. Meta-evaluation of benchmarks themselves is becoming more common. Researchers analyze whether benchmarks contain annotation artifacts, spurious correlations, or demographic biases. In some cases, models achieve high scores by exploiting dataset quirks rather than learning the intended skill. Detecting and fixing these issues is an ongoing effort. It is also useful to distinguish between academic benchmarks and industry evaluation suites. Academic benchmarks tend to be public, standardized, and widely shared. Industry evaluations may be proprietary, tailored to specific products, and focused on real-world performance metrics. Both play important roles, but they serve different optimization targets. For highly technical practitioners, the key takeaway is that benchmark scores are measurements with context, not absolute truths. Proper interpretation requires understanding the dataset construction, metric properties, statistical uncertainty, and potential failure modes. A model that leads a leaderboard is not automatically the best model for every application. As AI systems become more capable, the community is also grappling with evaluating higher-level reasoning and agent behavior. Static question-answer benchmarks may not capture multi-step planning, tool use, or long-horizon coherence. New evaluation paradigms involving interactive environments and programmatic task suites are emerging, but standardization remains in progress. Another frontier is safety and alignment benchmarking. Beyond task performance, researchers increasingly evaluate models for harmful outputs, bias, hallucination rates, and controllability. These dimensions are harder to quantify and often require carefully designed human-in-the-loop protocols. Benchmark governance is also becoming an important topic. Who maintains the dataset? How are errors corrected? When should a benchmark be retired? Long-lived benchmarks accumulate technical debt, including annotation mistakes and outdated distributions. Some communities now adopt versioning schemes or periodic refresh cycles. For practitioners building real systems, one practical lesson is to avoid optimizing exclusively for public benchmark scores. Internal evaluation that mirrors the target deployment environment is essential. Benchmarks are useful proxies, but they are rarely perfect mirrors of real-world complexity. For researchers, benchmarks remain indispensable. They provide the shared language through which progress is communicated. But mature use of benchmarks involves skepticism, statistical rigor, and awareness of their limitations. Looking forward, the field is moving toward more holistic evaluation frameworks. Instead of single-number leaderboards, we are likely to see multidimensional evaluation dashboards capturing accuracy, robustness, efficiency, safety, and calibration simultaneously. This reflects the growing recognition that intelligence is not one-dimensional. In summary, benchmark datasets and leaderboards are the measurement backbone of modern AI. They enable rapid progress, reproducibility, and transparent comparison. At the same time, they introduce incentives and artifacts that can distort research if interpreted naively. A technically sophisticated understanding requires viewing benchmarks not as definitive judgments, but as carefully constructed experiments with assumptions, noise, and evolving relevance. The most effective practitioners treat leaderboard performance as one signal among many, always grounded in a deeper understanding of what the benchmark truly measures and what it leaves out.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.